Hi there, it's Chem Coach Powers, and welcome to another chemistry lecture. Today we are going to be talking about section 11.1. We're talking about gas pressure and Dalton's law of partial pressure. So let's go ahead and jump into it, and I think you're going to enjoy some of the stuff we're talking about today. All right, so these are our objectives. We want to define pressure, convert from one unit of pressure to another, define STP, and state and solve problems using Dalton's law of partial pressures. We want to explain how pressure is generated through the collision of gas molecules, convert from kilopascals to millimeters of mercury or atmosphere, state the conditions of standard temperature and pressure, and given the partial pressures in a mixture of gas, I can determine the total pressure. Okay, that's kind of what you're trying to do here today. Now, the first three of these we've pretty much hit before, so it's going to be review. That last one, Dalton's partial pressure, we're going to hit that one in a little bit more detail. Now, as we get going into this chapter 11, I want to really quickly review what we talked about in chapter 10 at the beginning, because it's going to be really important as we hit chapter 11 again, okay? So it's just a real quick review of the kinetic molecular theory. Remember, KMT, we want to start being able to express so much of the stuff we do in chemistry with respect to the KMT, right? We want to make sure that we can see solids, liquids, and gases in terms of particle motions. And especially now we're hitting gases. Now, in chapter 10, we talked about an ideal gas. Now, an ideal gas is a hypothetical gas that fits all the assumptions of the KMT. An ideal gas doesn't exist, okay? Let's just get to that right away. Ideal gases aren't a thing. However, we use this concept of ideal gases to describe what happens to gases, because many gases approach ideal behavior, and it helps us to do the math if we can assume ideal behavior. All right, so what does that mean? What does an ideal gas mean in terms of the kinetic molecular theory? That the particles of gas are very spread out compared to their size, that the collisions are completely elastic, all right, so they bounce off of each other without any loss of energy, and then they are in constant random motion. Okay, and again, these things, as you're thinking about them, you're like, yeah, it doesn't seem to work with the laws of physics that I understand. And no, they don't, all right? You cannot have a perfectly elastic collision with two gas particles. However, you can have some very little energy given off or lost. And so we assume these things because, you know, they don't really collide that often, right? Comparatively to liquids, probably not, right? All right, and then no forces of attraction or repulsion between the particles. Again, the gases are able to stay apart. They're not coming together and being attracted and then becoming a liquid, right? Again, this is an ideal gas. And then the average kinetic energy is going to be a direct result of what the temperature is. Those two are connected to each other, all right? Kinetic energy and temperature totally connected to each other. All right, so the KMT explains the expansion of gases, that they don't have a definite shape or volume, okay? They fill whatever container they're in. It explains their motion, right? So there's no attraction, so they just continue to randomly go wherever. It explains their fluidity, okay? Again, there's no attraction between them, and so they're not gathering together and collecting and staying still, right? They're just continuing to flow around each other completely. It explains their low density. Particles are really spread out, so they're not very dense. It explains their compressibility. Again, particles are really spread out, so you can push them together a lot. And then diffusion and effusion. Remember, we talked about a diffusion and effusion a little bit in the last chapter, but make sure you have these definitions now. The spontaneous mixing due to the random motion, make sure you know that. And then effusion is being able to pass through that tiny little hole. So you can see these gas particles over here, okay? And when a gas particle can go through this little hole, there's a little wall here. And so there's a little hole that's here. So if a gas particle can go through that hole, then that is what we call effusion, process by which gas particles pass through a tiny opening, all right? In this example, you can see diffusion. Particles are pushing through in both ways from that direction, and then these particles are moving in this direction. Eventually, they're all going to completely spread out and be mixed in together fully, right? All right, so let's talk about this a little bit. This is a think, pair, share if we were in seat. But right now I want you to just think and don't pair and share with yourself, okay? If there is no such thing as an ideal gas, why do we do equations that assume the properties of an ideal gas? And I kind of talked about that already when I just mentioned it just a second ago. So think about that. And maybe if you want to pause, you can, because I'm going to give you the answer. Okay, you're back. So the reason is so that we can do these mathematical equations. Okay, we're going to be doing a lab where you are looking at the ideal gas law, right? There's this law, which is a mathematical equation here, and we're going to be taking a look at that and seeing if we can describe, what the volume is if we know the number of moles, and we have a few different things we're going to talk about, but you want to be able to apply mathematical formulas. And so we use the ideal gas so that we can make predictions about, unknowns, for instance. And again, these gases that we are going to deal with are closely approaching an ideal gas. Not all gases do, but many of the gases with non-polar molecules can approach this ideal property. So it's an okay thing to assume, so we can get really close to the numbers. Even if they're not perfect numbers, they're really close. All right, so let's talk about pressure. Now, when we talk about pressure, we've got to know that we're talking about collisions. All right, I really want you to think in terms of collisions when you're thinking of pressure, because that's basically what's happening. The collisions of the gas particles with the sides of the containers, right? So that's basically what we want to think of. Collision of particles with sides of the container, whatever that container might be. Okay. All right, so what's our equation? Pressure is equal to the force divided by the area. The area of that container, will be on bottom, and then the force. And the force is expressed in newtons. And so when we actually come up with the final answer to this pressure value, we're going to have a few different units that we're talking about. But if we're talking about force in newtons, then pressure is going to be expressed in kilopascals, pascals or kilopascals. So why is it easier to pop a balloon with a sharp object rather than squeezing it with your hands? Well, think about the pressure. The tiny, tiny, tiny amount of pressure that is being put on the tip of that pin is going to be much greater because it's at a small surface than your hands, which are going to have a much larger surface area. So you can put a lot more pressure on that balloon with your fingers, right? But it's spread out over a bigger area. You take a small little pin tip and you put it seems like a tiny bit of pressure, but the actual pressure would be greater with that pin. Why? Because this area would be so much smaller, right? The force might be smaller, but the area would be smaller, and the pressure is going to be much greater with that small little pin. Okay, so again, collisions, all right? Focus on that word there, collisions. The more collisions you have, the higher the pressure. And remember that the pressure that's exerted by a gas depends upon volume, okay, temperature, and then the number of molecules present, which we're going to use later on. We're going to use the N, or basically you can think of that in terms of moles, okay? All right, so the atmospheric pressure. What is atmospheric pressure? We just got to think about the fact that the Earth is surrounded by all these gases. And so you have collisions of these gases with the surface of the planet, right? And so all of these particles are striking the surface of the planet all the time. And that's where we get this pressure, okay? It's 1 atmosphere is a typical pressure unit that you're used to hearing about, but it's also 101.325 kilopascals, or kilonewtons per meter squared, okay? And that's our pressure. So lots of pressure on, from all the gases that are on top of the Earth, and that is considered 1 atmosphere of pressure when you're at sea level. Now, how do we measure pressure? We have 2 devices that we want to talk about. One is a barometer, and the other is the manometer. Now, barometers and manometers basically use the same technology, right? But the barometer is measuring the pressure of the atmosphere, and the manometer is using an enclosed container and measuring that pressure. Now, what's happening here is we have a tube of mercury, okay? And if this is a manometer, we might have a bunch of gas particles that are being created in here, and they're pushing on the mercury. Now, the height that that mercury rises from its base level to wherever it finishes, that is going to be its change in pressure, right? The change in height is basically equal to the change of pressure. So this mercury is going to be able to tell you the amount of pressure that's involved in this particular manometer. Now, barometer is going to do the same thing, but it's just measuring the atmospheric pressure, okay? So here we have the pressure of the atmosphere pushing down. And you'll notice that we've got this little, pool of mercury down here. This is an open little tube that connects here. And we are pushing this mercury up into the tube. So as this tube rises, as the mercury in this tube rises, then you're going to have that basically meaning that there's an increase in pressure. Now, it's important to keep in mind that this is a vacuum. And I want you to think about why that's a vacuum. I'm about to ask you that question. Why does it matter that this is a vacuum? What would it mean if there were gas particles in here? Okay. What would it mean if this solution was made out of water or gasoline or something instead of mercury? Would that be different? Would we have a different number of gas particles in here than if we had mercury? Think about those things. Okay. So that's a barometer. And you'll notice that the name of some of these measurements are very practical, and some of them are named after people. So I didn't say what this was really quick, but when you hear, from the news, you might hear 29.92 inches of mercury, but in science class, you might say 760 millimeters of mercury. We're actually talking about the distance. If we had a meter long tube here, it would be rising up 760 millimeters to demonstrate what normal atmospheric pressure is at sea level. And so we're actually coming up with these numbers based upon the actual height that the millimeter, the mercury is rising. Okay, you guys have heard of mercury rising. Usually talks about temperature when we talk about mercury rising. All right, so why is it important to have a vacuum above the column of mercury? Go ahead and pause for a second, see if you can think of it. And you're back. And the reason is because if we had all that gas up in this area up here, remember I told you, think about this gas up here, then that gas is going to, compress, but the more gas you have up here, the more it's going to push back down. And we don't want any pushback at all. And that's why we use mercury instead of water or gasoline or some other substance. We want to make sure that because mercury is very, very, very low volatility, it doesn't like to evaporate, right? It's really strongly held to itself with its surface tension. Then it's so cohesive, it's not going to really evaporate. And so you get much better, much more accurate readings if you use mercury compared to like water or something. All right. So that answers those two questions. There we go. Intermolecular forces at play. So let's look at our units of pressure and which ones you should be able to convert between. So we've talked about millimeters of mercury already. We've talked about pascals or kilopascals. We've talked about atmospheres. You guys are also familiar with PSI, pounds per square inch, right? And then one that you'll see in atmospheric weather reports oftentimes is a bar. Now the torr is exactly the same as a millimeter of mercury in terms of the actual numbers of those. They convert equally to each other. Torr is named after Evangelista Torricelli, who basically invented one of those barometers. Okay. Now you'll know that you have to look on page 344. Okay. There's a chart on page 344 that has conversion factors between a lot of these different pressure units. And so you can refer to that at any point you need to. So what are our most common ones? You should know these, right? You should have these memorized because we use these a lot. So keep those in your brain. There are exactly 760 millimeters of mercury in one atmosphere. There's 101.325 kilopascals in one atmosphere. There's 101.325 kilopascals in 760 torr, right? So know how to convert between each of those. Those are important. All right, so let's see if we can do a problem here. It says the average atmospheric pressure in Denver, Colorado is 0.830 atmospheres. Express this pressure in millimeters of mercury and kilopascals. So these are just unit conversion factors. All we have to do is use one of these values here, okay, the values that we had here. We're just using those to convert from one substance to the next, and it'll be easy. We just got to make sure we put on bottom what needs to cancel out, right? And then we go from there. So let's start with our given. Atmospheric pressure is 0.830 atmospheres. Our unknown, okay, is that the pressure in millimeters of mercury and the pressure in kilopascals. We've got to substitute. You do not have to use a formula for this. You can just use straight unit conversions. Just throw in that unit conversion right there and then multiply out, and you're going to end up with your answer. So 0.830 atmospheres is equal to 631 millimeters of mercury. and it's equal to 84.1 kilopascals. Again, you'll notice that we use the 1 atmosphere on bottom there, but the value, okay, it's one bottom for both of those, but the value of the conversion factor on top was different, so that's what would give us those different answers. Okay, so let's see if you can do this on your own, all right? Vapor pressure of water at 50 degrees Celsius is 12.33 kilopascals. What's this value in millimeters of mercury? And then the next one, the critical pressure of carbon dioxide at 72.7 atmospheres. What's this value in units of kilopascals? All right, so we're going to pause and practice and see if you guys can get this. Pause. And welcome back. Let's see what you did, okay? So, you know, some information here right now that's actually extraneous when it comes to a quick conversion is that 50 degrees Celsius. So we can just start with 12.33 kilopascals, and then we just do a unit conversion factor, and that unit conversion factor is going to take us from kilopascals to, they wanted millimeters of mercury, right? So we just do mmHg. Kilopascals has to be on bottom, so it cancels out, and it's 101.325 kilopascals for every 760 millimeters of mercury. Okay, so we're going to have to multiply that out, and we'll get our answer. It doesn't sound like it's going to be too tough, right? 12.33 times 760 divided by 101.325. And that's going to give us an answer of 92.48 millimeters of mercury. Now, it's important that we have the right number of sig figs, right? We have 4 sig figs here, so we're good with 4 sig figs here. This one doesn't matter in terms of the 3 sig figs it had because it wasn't even part of our problem. And when you see this value here, you're like, well, that's only got 2 sig figs. Yeah, but remember that whenever we do unit conversions, we assume that these conversions are infinite number of sig figs. Even if they're not, we just make that an assumption since we don't necessarily know what those conversions are. If you were doing some quantitative science, you'd want to make sure you got the exact conversion. But for right now, we just assume that those are exact amounts. All right, so the next one, critical pressure of carbon dioxide, 72.7 atmospheres. And now we need to know what that is in kilopascals. Well, again, what do we want on bottom and what do we want on top, right? We want kilopascals on top. So we know there's 101.325 kilopascals, and that's equal to 1 atmosphere. Just knowing those is really important for the test, for instance. Atmospheres cancel off, so what we have to do is multiply 72.7 times 101.325, and we get the answer, 7,366.33. Now, how many sig figs do we have? We have 3 here, and it doesn't matter if this is a unit conversion, so we assume there's an infinite number there, so we have to go off of our original givens. So we just have to do 3 sig figs. Now, the only way to do that, we could either do it in scientific notation, or we can try to just express and round here. As we're expressing and rounding, we would round that 7, or that 6 up to a 7, so we'd be 7,370. And then we would do our values of kilopascals, okay? Whoa, I missed a number in there. 7,370, okay? So that would be our value, or you could do 7.37 times 10 to the 3rd kilopascals. Either of those would be great. Okay, so that's how you do those conversions. Hopefully you guys were able to figure that out pretty easily. Some pretty basic math. All right, we did that. Done. Yeah, so I get this answer again would have been incorrect up here. That would have been incorrect because you actually can go 4 sig figs on that one. So 92.48 is a better answer. All right, so let's talk about STP. These are the standard conditions for purposes of comparison. We're dealing with 20 degrees Celsius and 1 atmosphere of pressure. Just memorize that. You need to know because there will be many times when you're going to have to know that the experiment was done at STP and you know what those conditions are. So basically, that's just like a baseline of let's do 1 atmosphere and then 20 degrees Celsius, which is a little, it's about room temperature, a little maybe cooler, but about room temperature. And you just say, all right, well, this is what we're going to do our experiment at, and then we can compare it. And so it's just a quick, easy way of giving us a couple numbers that everybody memorizes without having to actually say those numbers. All right, so then our last thing is Dalton's law of partial pressures. Now, Dalton's law of partial pressures is a really cool concept that helps us to understand what some of our errors might be when we're trying to figure out the amount of gas that we collect over a liquid container, all right? The idea here is that, that the gases, pressures add up together to give you the cumulative gas pressure, right? So each of those individual little particles, whether it be a big particle or a little particle, each of those particles are going to contribute somewhat to the pressure as it collides against the container surface. And so the partial pressure is the combined pressure of all the different collisions of all the different types of gases. All right, so for instance, the partial pressure of nitrogen in air, nitrogen is only one of the many gases that are in air, right? And so you could ask yourself, what's the partial pressure of nitrogen? And you'd have to figure out, well, what is the nitrogen component versus all the other gases? You'd have to kind of break up what percentages of each of those gases were. Okay, so here if I have gas A, gas B, gas C, and each of those has, if you just look at it, each of them has their number, right? So this has got 5 particles in it, that's got 5 particles in it, and that's got 5 particles in it. And so having 5 particles in each one, if we look down here, we combine all those gases into the same chamber, now they have 15 particles in the same amount of space. So you have to add up the collisions of each of those 5 different particles from each of those containers, because now they're all sharing the space, and so now they're going to have more collisions. So you add up their overall pressures, and this is Dalton's law of partial pressures. The total pressure is equal to the pressures of, or the sum of the pressures that are making up the gas mixture. Okay, so that's Dalton's law of partial pressures. Now, let's have you think about this again. We don't have a partner to practice this necessarily with right now, but you're going to think about a liter containing oxygen. Okay, and that is at a pressure of 101 kilopascals. The nitrogen, which is at 202 kilopascals, and then you have hydrogen gas at 303 kilopascals. All right, so I want you to think about transferring the oxygen and nitrogen to the container occupied by the hydrogen. What will be the pressure of the oxygen in the final mixture? Now remember, the pressure of the oxygen is not going to change, right? Pressure of oxygen is 101 kilopascals. That has to do with the number of collisions that oxygen makes with the size of the container. And so that pressure stays the same. However, the total pressure, we now have to add up all of these, right? So we actually have the, okay, as long as we're still in a 1 liter container, right? These are all in 1 liter containers. As long as we still have a 1 liter container, we now have 606 kilopascals, because we've got to add up all those different collisions that are in that particular container, right? So the total pressure is going to go up because you have to add up the individual pressures. All right, so when we do experiments, a lot of times we're going to do experiments in a scenario which is called water displacement. Now, you're going to see a picture of this here in a second. But basically, we're bubbling up this gas that we've created, and we're collecting the gas in a container. But because it's bubbling up through water, that water is now evaporating, and it's filling up the container a little bit itself. And we have to account. If we want to know how much gas do I have in here of this substance I'm collecting, well, how much of that substance, that material inside that flask is now water from being bubbled up, because water's evaporating, right? All right, so we collect gases over water. That's a typical process in the chemistry lab. And because we do that, it's going to, and you'll see the example here, it's going to displace the water, and it's going to fill it up with the gas. And so we have to calculate what percentage of that new gas that's filled into this container is going to be water vapor, right? Because of evaporation. And so that pressure that the water is giving off, because you're sitting right above water, is called the vapor pressure. And we learned about that last time when we talked about boiling. All right, so here's the idea. Okay, you've got this gas collection bottle, and this gas collection bottle starts filled up completely with water. The reaction is taking place here, right? Let's say I put in some acid, right, into a container that had some zinc. I poured it in, and now all of this gas is bubbling. All right, now this is have a one-way valve. It doesn't let the gas escape back out. So all that gas is going through here. So this is bubbling up some gas, and as it bubbles up the gas and it comes through here, that gas is now filling up. Its little bubbles are traveling up to the top of the container, and eventually they're filling up the space up here with air, right, with gas. And so whatever that gas was, in this case, that gas would be hydrogen gas, right? So from this reaction, you can see that little H2. That hydrogen gas would be filling up inside this container. and the water is getting displaced. The water level is dropping, and it's filling up this little pool a little bit higher, a little bit higher, okay, because the gas is displacing the liquid that's in here, okay? Now, what does this little area inside here look like? Well, they've done a little zoom in over here, okay? Now, this little area has the gas you're looking for, which is the hydrogen gas, but look, it's also got water particles in them as well. And so this water vapor is actually being collected with the hydrogen gas. And so we're going to have to use Dalton's law of partial pressures to figure out how much of that collected material is actually water vapor and how much is the hydrogen gas. All right, so we take a formula like this and we say the pressure of the atmosphere, okay, because if we look at the atmosphere out here, this is atmospheric pressure that's pushing on all of this, right? Atmospheric pressure is pushing down. And so the atmospheric pressure is going to be pushing on this, and whatever pressure's in here has got to push back with an equal amount of force to make this liquid come up. And so the pressure in here is equal to the atmospheric pressure, okay? If that seems a little bit confusing to you right now, just trust me on that one. The pressure inside the container is equal to the atmospheric pressure. So the atmospheric pressure is equal to the pressure of the gas plus the pressure of the water. Now, we don't know what the pressure of the gas is, but we can tell you the pressure of the water. Why? Because we can do this experiment in many different environments, and we can actually look and find the pressure of the water from a table, okay? All right, so this is basically just saying, this is, all Dalton's law of partial pressures that helped us figure this out. The pressure of the atmosphere is equal to the pressure inside the bottle, and we'll have to look up the value of the pressure of water in a table in your book. And then you'll be able to calculate the pressure of the gas. Where do we get the pressure of the atmosphere? We get the pressure of the atmosphere from a table, or from, well, not from a table, from a barometer, or from the, well, I was thinking of the table on the internet because I can just look it up on the internet, right? And see what today's daily pressure is in my area. You can do local weather report pressures. All right. So let's look at an example of a collection of collection of gas by water displacement, okay? Oxygen gas from the decomposition of potassium chlorate was collected by water displacement. The barometric pressure and the temperature during the experiment were 731.0 torr and 20.0 degrees Celsius, respectively. What was the partial pressure of the oxygen collected? All right, so we're going to do this example together first, and then you'll try one on your own. First of all, you got to look in your book for the partial pressure of water at 20 degrees Celsius, okay? So I'm going to tell you what page that's in, but first I'm going to take a little break and I'll be right back. And welcome back. So what I did is I went and I got the textbook, and in the textbook I went to the back in the different appendices and and I found page R63 has a table B-8. And it's basically called water vapor pressure, and it's a bunch of different numbers listed there. Now, what I'm going to do is I'm going to look at the 20-degree value over on the left-hand column under temperature, and then I cross over to the middle column where it says pressure in millimeters of mercury, because millimeters of mercury and torr are the same units. And so I'm going to be able to use that number, and that number is going to plug into my partial pressure value for solving this problem, the partial pressure of the oxygen collected. All right, so here's what it looks like. I looked that up on, and again, did I say, page R63, I think I said that already. So we'd see that our partial pressure of H2O is going to be 17.5 torr at 20 degrees Celsius. And again, all these values are for 20 degrees Celsius. That value is for 20 degrees Celsius, and it's all in pressure of millimeters of mercury and pressure in kilopascals for this particular text. And then you would say, okay, well, if 17.5 is my pressure for water, I'll plug that in there. My formula is the P total pressure is equal to the pressure of the oxygen plus the pressure of water. And so I know my total pressure at 731.0 torr, so now I can solve for my pressure of oxygen. And so that will give me a value. What is my oxygen? My oxygen pressure is actually 713.5 torr. Okay, so that's how you solve these problems. So now it's your turn. Let's see how you do. A sample of nitrogen gas is collected over water at a temperature of 23.0 degrees Celsius. what's the pressure of the gas? The atmospheric pressure is 785 millimeters of mercury. And then it gives you, so you don't have to look in the book, it gives you the pressure. It says at 23.0 degrees Celsius, the vapor pressure of water is 21.1 millimeters of mercury. Okay, so why don't you pause and practice and we'll see how you do. Pause it. And we're back. Excuse me. So let's see what you came up with. First thing you've got to do is, write out your givens and your unknowns, and then write your formula, right? So this is the formula. Our givens and unknowns, right? We've got our givens being 23.0 degrees Celsius is our temp. Okay, and that's the value we're going to have to use to look up our temperature in our book for our pressure. Excuse me. And then we've got 785 millimeters of mercury, and that says that's the atmospheric pressure. Remember that the atmospheric pressure is going to be equal to the total pressure, because when you're doing the gas collection over one of these little containers, then the gas collection is going to equal the atmospheric pressure. So we've got our P total. We're going to look up in our book to find our P of water, and now we can solve for P of nitrogen. So our unknown is P of nitrogen. Okay. So we'll just put a little n there. And then what units are we going to use? Let's just go ahead and just stay in millimeters of mercury, because that's what they've given us to start with. Okay, so let's look at the rest of the problem then. So we plug it in to that formula. 785 is equal to 21.1 plus P nitrogen. If we wanted to, for the M step, the manipulate step, we could have said, all right, well, P of nitrogen is equal to, and then you would have just done the P of the atmosphere minus P of the water, right? And that would have given you your answer there. So you get a value of 764 millimeters of mercury. You've got 3 sig figs all around, so you're good to put that as your partial pressure of nitrogen. Okay, so that's how you solve those problems. Hopefully you got that one right, and you are a rock star now for solving partial pressure problems. Oh, it's a hard to say. Partial pressure problems. Everybody say that real quickly, very quickly. 5 times, right? Partial pressure problems, 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 partial pressure problems. I know you are so happy that you just got to waste some of your time listening to me say that 5 times. But I got to hear you say it too 5 times, because you did that, right? No, you didn't. Don't lie. Well, some of you did. All right. Define pressure. These are our objectives review. Yes. Force divided by area. We can now convert among units of pressure because we know our unit conversion factors. Remember to memorize those. STP, standard temperature and pressure, 20 degrees Celsius and 1 atmosphere. State and solve problems using Dalton's law of partial pressures. The total pressure of all of the gases is the sum of the individual pressures in a mixture of gases. And so now, can you explain how pressure is generated through collisions of gas molecules? Yes, because every molecule has mass, and every molecule as it strikes into something is going to apply a force, right? And so force divided by area is going to be the pressure. If I give you pressure in kilopascals, 101.325, millimeters of mercury, 760, or atmospheres, 1, you can convert to any other pressure of unit. You can state the conditions of standard temperature and pressure. Let's try it again. 20 degrees Celsius, yes, 1 atmosphere, or 101.325 kilopascals, 760 torr, 760 millimeters of mercury, 14.2 psi. All right, given the partial pressures in a mixture of gases, you can determine the total pressure. You don't have to know the psi one. Yeah, you can do that with Dalton's law of partial pressures, right? Okay, so you guys have gotten it. You're rock stars, and we're gonna let you out of here and free you from the learning that you've been doing. And yeah, that's all I got to say. Have a great day. God bless you. Be kind to one another, because that's the way to be.